Hello viewers, so we meet again with a new lecture on binary search tree. So what is a binary search tree? A binary search tree is a binary tree in which nodes are arranged in a logical way depending upon the elements stored in it. This means each element in left subtree is less than its root element, each element in right subtree is larger than its root element. Both the left and right subtree of root will again be binary search tree. In short, we can say that left child is always smaller than its parent and right child is always larger than its parent. In case there are equal elements, then the replicated element can be in left subtree or right subtree. But one order must be opted, say every replicated element should be in the right side. Looking at the given binary search tree, the elements in the left subtree of root are 15, 7, 22, 18, 30 and 20. These all elements are smaller than root element 40. The elements in right subtree of root are 80, 60, 100 and 90. These all elements are larger than root element 40. A very important characteristic of binary search tree is that when we traverse it in order, it produces a sorted list of elements in ascending order. If we traverse the shown binary search tree in order, it gives the order 7, 15, 18, 20, 22, 30, 40, 60, 80, 90 and 100, which is in ascending order. In other words, we can say that if the in order traversal of a binary tree comes out to be in ascending order, then that binary tree is definitely a binary search tree. Binary search tree is so called because it is a binary tree and has a search property. This search property is the key that make binary search tree and its variants a very efficient data structure. The variants of binary search tree are AVL tree and red black tree. So let us see what this search property is and what makes it so efficient. Binary search tree enable us to locate the desired element in a very efficient manner as compared to any other data structure. To search for a particular element, we start at the root by comparing the desired element with the root element. If both are same, then search procedure is stopped, otherwise we follow the left branch or right branch depending on whether the desired element is smaller than or larger than root element. This procedure is repeated recursively until we find the desired element or we conclude that element is not present in the binary search tree. To understand the search procedure in binary search tree, look into the binary search tree in which we want to search for the element 55. Here, first of all, we compare the desired element 55 with the root element. As the desired element is not same as root element, so the search property of binary search tree says that the element 55 might be in right subtree because desired element is larger than root element. And we know that the elements in right subtree of root are larger than root element. So, in right subtree we compare the element 55 with the root of right subtree, which is 80. Here we move to the left subtree of node 80. This is because the desired element 55 is smaller than element 80. In left subtree of 80, we compare the element 55 with the element 60. As both are not equal, so we move to the left subtree of 60 as the element 55 is smaller than 60. In the left subtree, the desired element 55 is compared with the node which also contains the element 55. Here our search is successful. We have got the desired element and we stop our search here. Let us look at another example. Here we are to search for element 25. Comparing it with root element 40, we move towards the left subtree because 25 is less than root 40. In left subtree, 25 is compared with 15. Now, we move towards the right as 25 is larger than 15. In the right subtree, we compare 25 with 22 and again move towards right, where we compare 25 with 30. Here, as the desired element 25 is smaller than 30, so we are to move towards left. But as shown in the tree, the left child of 30 does not exist. So we stop our search and declare that the desired element 25 does not exist in this binary search tree. The search operation in binary search tree is very efficient and it depends upon the height of binary search tree. You know, the height of tree is the length of the longest path from root node. So, the complexity of binary search tree is big O H. Look at the diagram. The number of comparisons that took place to declare that desired element is not present is 4. Even the maximum number of comparisons that could take place to find an element or to declare that the element is not present is 5, which is height of the tree plus 1. Here the height of the tree is 4 because the length of the longest path from root node is 4. Here the longest path from root node is 40 to 15, 15 to 22, 22 to 18 and 18 to 20, which is of length 4. As the height of the tree increases, the running time to search the element also increases. If the height of the tree is of order n, where n is the total number of nodes, then running time becomes linear. Look at the figure. Here the binary search tree has 7 nodes and height of the tree is 6. Here the running time of search operation is of order n, that is number of nodes in the tree. This is the most inefficient case of search operation because binary search tree is not balanced. The tree is said to be balanced if the height of right and left subtree of each node is equal. Here is an example of balanced and unbalanced binary search tree. Binary search tree shown in the left side is balanced binary search tree because the height of left subtree and right subtree of each node is equal. The binary search tree shown in the right side is not balanced because the left subtree of root has height 0, whereas right subtree of root has height 2. As the height of left and right subtree of root are not equal, therefore, this tree is not balanced. Let us move to the insertion operation in binary search tree. One thing must be taken care that while inserting a new element into binary search tree, the properties of binary search tree must be preserved so that the tree remains a binary search tree after insertion of new element. Before inserting the new element, the appropriate position for inserting the new element is required. To get the appropriate position, search operation is performed. After the appropriate insertion position is found, the new element is inserted there. It must be noted that the insertion of new element always take place as the leaf node. To understand the insertion operation, consider the binary search tree. Suppose an element 55 is to be inserted in this binary search tree. Before inserting the element 55 into the tree, we will find the appropriate position where it can be inserted. To accomplish this task, we will start comparing the element 55 with root element 40. As element 55 is larger than root element, so we proceed towards the right. Now, we compare the element 55 with element 80, which is the root of the right subtree. At this stage, we will proceed towards the left subtree as 55 is less than 80. Now, compare the element 55 with the element 60. As the element 55 is less than 60, there is no left child of this current node. Therefore, the element 55 will be inserted as the left child of the current node 60. Again, the point must be noted that the insertion of the new element always take place as a leaf node. Just like the search operation, the running time of insertion operation is also of order h, the height of the tree. This means lesser the height of the tree, lesser will be the time for insertion operation, because there will be lesser number of comparisons. Let us look at another example. Here the new element 16 is to be inserted into binary search tree. So, comparing 16 with the root element 40, we move towards left. Then comparing 16 with 15, we move towards right. In the right, compare 16 with 22 and we move towards left. In the left, we compare 16 with 18 and move towards left. But the left subtree of 18 does not exist, so we insert the new element as the left child of node 18. Now, let us discuss the deletion operation in binary search tree. Again, it must be taken care that after deletion of a node in binary search tree, the properties of binary search tree must be preserved. The first step for deletion of a node from binary search tree is to locate the node and its parent node. Here we will apply the search operation to find the node to be deleted and its parent node in binary search tree. After locating the node, we will apply the deletion process depending upon three conditions. The first condition is the node to be deleted from the root may be a leaf node, that is, it does not has any child. Secondly, the node to be deleted has one child, and thirdly, the node to be deleted has two children. Let us discuss the first case when the node to be deleted has no child. Look at the binary search tree. Here in this binary search tree, it is very simple to delete any of the leaf nodes 20, 32, 43, 55, 70 and 120. Once we search the node to be deleted and its parent node, only one pointer field in the parent node is required to set to null. For example, if we want to delete node 32 in this binary search tree, we need to set the left pointer field of node 35 to null. Of course, node 35 is the parent of node 32. Let us discuss the deletion of node having a single child. The deletion process is still simple if node to be deleted has one child. To delete a node which has only one child, it will be replaced by its only child element, no matter whether the only child is left child or right child. For example, the items 35, 42 and 100 in the binary search tree shown here have only one child. Here, to delete the item 42 from the tree, the node 42 will be replaced by its only child 43. Technically, the right pointer field of node 40 is set to the address of node 43, which is in the right pointer field of node 42. Let us discuss the third case of deletion, where the node to be deleted has two children. The process of deleting such a node that has two children become complex, as in this case we have to find the in-order successor. Yes, in-order successor of the node to be deleted will replace it. The question is what this in-order successor is and how to get it. Successor means given a particular key and we have to find the next one. Consider the binary search tree. Here, consider the node 30. The in-order successor of 30 is 32, because 32 is the element which is just larger than 30. Similarly, consider a node 50. The in-order successor of 50 is 55, as there is no element between 50 and 55 in this binary search tree. Here, the term in order is used, which means that we traverse the tree in order manner. We get the element in ascending order. In this binary search tree, the in order traversal is 20, 30, 32, 35, 40, 42, 43, 50, 55, 60, 70, 90, 100 and 120. From this in order traversal, it is clear that successor of 50 is 55 and we call this successor as in order successor. The successor of 30 is 32 and successor of 40 is 42. Now, the question is how to get in order successor of any node. Logically, it is very simple to get the in order successor node. To get the in order successor, move to the right child and then move to the extreme left node. This extreme left node is in order successor. It must be noted that in order successor of any node will have no child or only one child. Yes, it is very important to state that the in order successor of any node will have no child or one child. If in order successor has one child, then definitely that child will be the right child. As if it has the left child, then this left child will be the in order successor. Let us have a clear understanding by considering a binary search tree. To find the in order successor of node 50, move to the right child of 50. Here we move to node 90. From node 90, move to the extreme left node. Here the extreme left node is 55, which is the in order successor of 50. Also note that node 55 has no child. Consider another example to find the in order successor of a node. To find the in order successor of node 50, move to the right child of node 50. Here we move to the node 200. From node 200, move to the extreme left node, that is from node 200 to node 160, then node 160 to 150, then from node 150 to 100 and then from 100 to 75. Node 75 is extreme left node, which is the in order successor of node 50. Also note that node 75 has one child, which is right child. In case 75 had the left child, then this left child would have been the in order successor, as it would have less than 75, but more than 50. Okay. We have got the idea of finding the in order successor of a node. This in order successor is the key for deleting a node having two children. As mentioned, the in order successor of a node has no child or only one child. This in order successor is deleted first, and the deletion of any node having no child or one child is simple operation and has already been discussed. This deleted in order successor will replace the node to be deleted. To understand the concept of deletion of a node having two children, look at the following binary search tree. Suppose we want to delete the element 30, which has two children 20 and 35. In this case, to delete the element 30, first step is to locate the in order successor of 30. Here the in order successor of 30 is node 32. Now, this node 32 replaces the node 30. Consider another example to delete a node containing two children. Suppose we want to delete element 50, which has two children 40 and 200. In this case, to delete the element 50, first step will be to locate the in order successor of 50. Here in order successor of 50 is node 75, which has one right child. This node 75 is deleted from here and node 50 is replaced by 75. It is very interesting to find the smallest element in the binary search tree. To find the smallest element in binary search tree, move to the extreme left node of the root node. This extreme left node contains the smallest element. This is because of the property of binary search tree that every left child node contains the element smaller than its parent element. So, the extreme left node will have the smallest element. Look into the diagram. Here in this binary search tree, we move to the extreme left of root node 50. That is, we move from node 50 to node 40, node 40 to node 30, and then node 30 to node 20. We have reached at the extreme left, which contains the smallest element 20. In the similar manner, we can find the largest element in binary search tree. To find the largest element in binary search tree, move to the extreme right node of the root node. This extreme right node contains the largest element. This is because of the property of binary search tree that every right child contains the element larger than its parent. So, the extreme right node will have the largest element. Look into the diagram. Here in this binary search tree, we move to the extreme right of root node 50. That is, we move from node 50 to node 90, node 90 to node 100, and then node 100 to node 120. We have reached at the extreme right, which contains the largest element 120. So, to end up, we have discussed about the binary search tree and its operations. We have seen that binary search tree has been a very efficient data structure in terms of search and insertion as compared to other linear data structures. So, thank you very much.